In this video, I will share the meaning of internal resistance of a cell and how to determine its value with the help of a potentiometer. First of all, what is the meaning of internal resistance of a cell? It is the resistance offered by electrodes of the cell and electrolyte that is used inside the cell. Both these portions oppose the flow of current through a cell. This opposition offered by these two things inside a cell is called internal resistance of the cell, and it is generally denoted by small letter r. For determination of internal resistance of a cell, we make use of a potentiometer. The T1 and T2 represent two terminals of a potentiometer. Its length may be 400 centimeter or 600 or anything more than that. The potentiometer can be operated by connecting it to a high potential battery through a resistance with the help of which sufficient amount of current can be made to flow through the potentiometer wire between terminals T1 and T2. Suppose this is a cell whose internal resistance is to be found. What we do, we connect this cell to the terminal T1 to which positive of the battery is connected. The positive of cell is also connected to the same terminal. Then this negative terminal of the cell is connected to a sensitive galvanometer. The other end of galvanometer is connected to jockey. Jockey used to make temporary connection with potentiometer wire. It can be slided over potentiometer wire. This is a circuit which can be used for finding internal resistance of a cell. Suppose current I is made to flow through the potentiometer wire. Then we slide the jockey over the potentiometer wire until galvanometer shows zero deflection. When galvanometer shows zero deflection at a certain position, suppose this distance of jockey from terminal T1, when this shows zero deflection, suppose this distance is L1, means at length L1 of potentiometer wire, our potential galvanometer represents 0 reading. As the galvanometer shows zero deflection, it means no current flows through this portion of circuit that is between T1 and galvanometer and jockey. And this zero current means potential of terminal T1 becomes equal to positive potential of the cell. So we can write at zero deflection position, potential of terminal T1 becomes equal to potential of positive terminal of cell, and potential of jockey will be equal to potential of negative of cell. So I can write potential of jockey J is equal to potential of negative of cell. So this is the position when no current will flow, because current flows only when two points are at different potential. When this potential point and this point are same potential, no current will flow. This point and this point are same potential, no current flow. As a result, there is zero deflection in the galvanometer. Using this, I can write potential difference between terminal T1 and jockey equal to potential difference between positive and negative of cell. That is potential difference between this terminal and this terminal, that is potential across portion L1 of potentiometer wire equal to potential difference between positive and negative terminal. This is positive terminal of cell, this is negative. Because no current is being drawn from this cell, in this position we can say potential difference between these two terminals is called EMF of the cell, and we denote EMF as this letter E. So using this I can write EMF of cell is equal to potential across this. Potential is given as current into resistance. Let me call resistance of this portion of wire as R1. So I can write EMF is equal to I. Resistance is of a wire is given as resistivity multiplied by length of the wire divided by area of cross section of the wire. So this is equation number 1, that is giving us value of EMF of cell by using this potentiometer wire. In the second step, we connect a high resistance of some known value, let's call it high resistance R, across the two terminals of cell, and again we move the jockey on potentiometer wire in such a way that galvanometer again shows zero deflection. Suppose in this case length of the wire at which galvanometer shows zero deflection is L2. In the previous step it was L1, and when we connect this resistance across this cell, some current will be drawn from the cell. Let me call this current as I dash. It will be drawn from the cell. When current is drawn from the cell, then the difference of the potentials of its two terminals is called potential difference. When no current is drawn, then this difference is called EMF of the cell. Again, because galvanometer is showing zero deflection, means potential of T1 becomes equal to potential of positive terminal, and potential of jockey becomes potential of negative terminal of the cell. So difference of the two potentials between T1 and J will be equal to difference of the potentials of positive and negative of the cell. So I can write potential difference between T1 and J in this situation will be equal to potential difference between positive and negative of the cell. Now potential difference between T1 and J, again by using Ohm's law I can write I into R2. Suppose in this case resistance of this portion is wire is R2. So I can write equal to potential difference between positive and negative, because current is being drawn. So difference of the potential will be equal to potential difference of the cell. Let me call it capital V. Now this can be written as V is equal to I. What will be resistance? R2, resistance of this portion of wire, again rho into length of the wire, L2 in this case, over area of cross section of wire, that will be same. So let me call it equation number 2. So from equation number 1 and 2 we can write the ratio of EMF of the cell to potential difference of its two terminals equal to L1 divided by L2. Equation number 3, where L1 is the position is the length of wire when jockey is at this position when galvanometer shows deflection without drawing current, and L2 is the length of the wire when we draw some current from the cell. Now let us have a look on this closed circuit. In this circuit, this E represents EMF of the cell, and this small r represents internal resistance of the cell. Capital R is external resistance that is known to us. I dash is current flowing in this circuit. By applying Kirchhoff law in this circuit, I can write EMF is equal to voltage across capital R resistance plus voltage across internal resistance, that is I dash into small r. Now EMF is equal to I dash into R means the resistance across this resistance. If this potential is same as the potential across cell, so this I dash R can be replaced by capital V, potential difference when current is drawn from it, plus I dash small r. Now how to find I dash? I dash means potential difference divided by resistance. By using Ohm's law, I can write this amount of current is drawn by this resistance multiplied with small r. By simplifying, I can write EMF is equal to V inside 1 plus small r over capital R. Just mathematics. From here, we can write EMF upon potential difference between terminals of the cell is equal to 1 plus R upon capital R. Equation number 4, let us suppose. If we compare the results of equation number 3 and equation number 4, so we can write 1 plus R upon capital R is equal to L1 upon L2. After simplification, we can get answer for small r equal to capital R into L1 upon L2 minus 1. So this is the required expression for internal resistance of a cell. Let me call it equation number 5. Now how to calculate internal resistance by using this? Let me again repeat. First of all, we are not to connect this outer resistance, means no current is being drawn from the cell, and we find the balance point by connecting a jockey, and this position, this length of the potentiometer wire is L1. Then we draw current. Again we repeat the same thing. When galvanometer shows zero deflection, suppose length is L2 and capital R is external resistance that is known to us. By putting these values, we can determine internal resistance of a cell by using potentiometer method. That's all.